We are going to cover public key cipher in the later chapter, and the meaning of public key cipher is we can share the key to everybody, which means everybody knows what key is dealing with to make the ciphertext. But still, it's kind of very difficult to break it or deciphering the text. So that's the kind of amazing part, and that is what we are really using at this moment, right? But this Pauli-Hellman cipher that we are going to cover in this chapter is not a public key yet, but it gives us a very good idea behind the public key cipher later. So it's very necessary to cover. And this is not for practical purpose, but more theoretical purpose to discuss, right? So let's just focusing on that one. And we call this kind of style of cipher is symmetric cipher because we use the same method to enciphering and deciphering. And for Pauli-Hellman cipher, we could use one of these two methods. Let's say P is a prime number, which should be really big number, and E times D is congruent to 1 modulo P minus 1. And of course, ED should be also very big number. Not one is really big and the other one is very small. Most likely same size numbers is going to be better. Then the first method is keeping all these three numbers P, E, and D secretly, right? So no one knows about it except the sender and receiver. And that's the one way we can do this Pauli-Hellman. And the second method is this large prime number P is public. Everybody knows about it, but it's very difficult to having the factors of it, E and D. That's the reason why we should have very big number for E and D, right? So that should be the secret parts of it. So the key for this method is just E and D. P is not included in our key because that is a public. So we could have this and either of them to make this handling this Pauli-Hellman. And it says because it's very difficult to make it or find it to have this large prime P. The second method is most likely the commonly used one. But as you can see here, if you know one big prime number which nobody knows about it, then your method is going to be very secure enough, really secure, right? And especially like ED is also really huge number. And even if both of them are prime numbers and nobody knows about this E and D, then your cipher system is almost unbreakable. That's why sometimes people, the government, try to hide these new prime numbers. You can guess, right? Because all the secret message and everything, if you use that new prime numbers which nobody knows, then no one could break it. Okay, so for this part, let's just check how difficult to find a large prime number. Okay? And if it's a try and error method, then you can see how long it's going to take. For example, this is 100 digit numbers. We don't know whether this is prime or not. So let's just try to take the factorization or just try to divide this one with some prime numbers. You can start from 2. Definitely it's not divisible by 2. How about 3? Okay, we have method, right? Just adding all these digits and checking whether the sum is divisible by 3 or not. Right? Definitely it's not. So just keep doing this way. Okay, how long is going to take, right? That's the question. Let's say we have a computer which could calculate 10 to the 12 numbers per second. which means let's assume we know all the prime numbers up to 10 to the 20 or 30 digits. Then let's say we could divide this number with each of that prime numbers starting from 2. Okay, so if my computer could calculate that much, and you know what, all these supercomputers could do this much only, right? Then every year we have 10 to the 8 seconds altogether. So the meaning is that this computer could calculate 10 to the 20 numbers per year. Okay, our number is 10 to the 100, but we already checked in the first chapter to check if the given number is prime number or not. We just try to divide that number up to square root of that number, right? Of course, with the prime numbers within that, right? So we could check only up to 10 to the 50 of them, right? I mean, please thinking about it. And we could calculate up to 10 to the 20 numbers per year. So if you divide it, we need that many years to just check whether the given that number is a prime or not. And 10 to the 3 is 1,000 years. So even I don't know how long this one is. So even you're using supercomputer, still it's almost impossible even just checking whether the given number is prime or not. So that's the difficulty we have at this moment. Even we could use the computers, and that's how we keep our security based on. Okay. Of course, you might think, okay, 10 to the 20 is not the real number. We just need that many prime numbers, right? So if you're assuming that, then it might be a little bit larger than this number. And you know what? It turns out, please use Maple program in chapter 1. If you cover up to 10 to the 21, that's almost 20 digits prime numbers you can find. So it's not a big deal. So still, it's almost impossible.